which is given by Paul Donaldson, and he will now speak about proteins in amide 1 band, the 2D-IR-Raman spectroscopy. So I will stop sharing and leave the floor to Paul.
Okay, I think that's set up, ready to go now. Right. Hi, everybody. What a great pleasure to come to these webinars. They're really making my Fridays much better. So thanks ever so much, Thomas and Maxime. And I take it you're getting a bit of help from other people too. And thank you to all of you for organizing these. They're really so welcome, especially during these times. So I expect that you don't have to buy your beer again at any CMDS conference. Hi everybody, and I hope you're all doing well right now. And I'm welcome to my talk on 2D-IR-Raman of the protein amide 1 band. And this is a talk that's really a summary of a paper that I wrote last year. Whoops, Daisy. Last year on this subject. So all the information that I present to you today, you'll find in this paper. And it's work that I did when I was an operations scientist at the CLF. So I was doing this very piecemeal and part-time on scheduled access to our facility laboratories over a couple of years. So getting a few weeks to build and then do a little bit of measuring and then take apart the experiments again. And then in the last couple of years, I've moved away from that sort of work and run my own group now. And that's given me time to actually consider what all this stuff means and write the paper. And special thanks to all these people who have inspired me and helped along the way. And in particular, Chris Middleton and his help with making our pulse shapers work was instrumental to this project. Right, so let us begin. I'm going to start with some pictures of Ben Nevis. So we're all interested in peaks. This is a different kind of peak. This is the highest peak in the UK. And my analogy to this subject of protein amide 1 spectroscopy and 2D-IR of it is that you know, this is probably the most popular mountain in the UK to climb. That normally there's about 150,000 ascents a year. And over the years, we have seen a lot of amide 1 spectroscopy, a lot of very high quality, very interesting things learned about the subject. And just like Ben Nevis, we've all looked and thought about this a lot. The interesting thing about Ben Nevis is that it looks like a hill from one direction, a very pretty hill. But if you look at it from another direction, from the north, it's very mountainous. It's a very different mountain. So although we're very familiar with Ben Nevis now and amide 1 spectroscopy, there's lots of different ways of looking at it. And I hope that maybe I'll show you a slightly different route up to the top where we see what the spectra are like. And I hope that that's enjoyable and interesting. Let me make a small adjustment to this. I don't think I can, but all right. So we've used a mountain analogy. So these are all the mountain walkers who do 2D vibrational spectroscopy labs all over the world. Sorry if I missed anybody, but this is all the special people whose knowledge and research has inspired and influenced me over the years. Down on this side, we have all the techniques where we're mixing visible and infrared pulses to generate two-dimensional vibrational spectra. And the work that I'm doing is very similar to work that has been done by these people over the years. And there's a lot that I've learned from their work, and maybe I hope vice versa. Why am I interested in 2D-IR-Raman? I've been coming to these conferences for years and giving 2D-IR-Raman mixed in with 2D-IR talks. But for the graduate students in the audience that haven't heard the arguments, that if we can combine some of the properties of 2D-IR, for example, the ability to look at the line shapes and get structural information from cross peaks, if we can combine them with some of the nice properties of Raman, like ability to look at very turbid or scattering media or very infrared optically dense media, then this could be a very interesting way of doing 2D-IR spectroscopy. And what I want to show you today is some of the properties of the method as we look at a very well-studied infrared band system, the amide 1 band. The two papers that in a way for me started it all, there's been lots of done work over the years, but John Wright has studied very intensively mixed infrared Raman processes and done a lot of experimental work. He calls the method that he invented for collecting the spectra DOVE. And Min Cho, again, around the same time, back in the late 90s, explored theoretically the possibility of measuring photon echoes with infrared Raman type processes. And these he explored in the time domain. John is very interested in learning how to do the spectroscopy in the frequency domain. And Min Cho calls his methods IR-Viz DFG. David Klug has been very prolific in exploring the DOVE methods as applied to looking at protein sidechain modes. And in his work, he terms this EVV, which fits in with the ethos of people doing VE and EV spectroscopy. I'm sort of calling these under an umbrella of 2D-IR-Raman. There are lots of different names for these methods. And if we're talking about the amide 1 band and its secondary structure, then obviously we're mostly looking at the difference between alpha helix or disordered protein backbone and beta sheet. And it's been known since the very earliest days of looking at secondary structure in protein that the infrared absorption spectra and the Raman emission spectra of alpha helical and beta sheet structures are very, very different to one another. And this is rationalized very early on as a transition dipole coupling effect, which directly reports on the secondary structure. And this beautiful model Hamiltonian scheme, just taking these energy terms and diagonalizing a correct structural matrix, has become very popular in the 2D-IR community and the infrared community for understanding these effects. And this all was taken advantage of in the earliest 2D-IR work from Robin Hochstrasser and Peter Ham in trying to understand how the coupling of the amide groups together affect the line shape, along with how much what's the nature of the broadening, how much is there inhomogeneity is there in this band. So the first time for us all to see one of these 2D-IR spectra, I think, was in this kind of paper, in this paper, and it was done through what is called a hole burning pump probe approach, which we learned later on very similar to the type of echo approaches that were being investigated back at this time. So, having just shown you possibly the first 2D-IR spectrum, let's very quickly do a recap on how they work and what they're comprised. So a 3-level anharmonic oscillator, you should find it all in the beautiful Harmanzani textbook, which I hope lots of you students have got and are looking at. And we look at the negative feature on the diagonal as comprised of stimulated emission and ground state bleach. And as you saw in Jennifer's talk earlier, where she showed the huge variety of different processes represented as double-sided Feynman diagrams, where we have the interactions from the fields noted here, and then the quantum states of the system that we go through. And in a 3-level anharmonic oscillator, we have 1 to 2 transitions, which are shifted lower in energy if the oscillator is anharmonic. And importantly, I think this figure is supposed to move, but it doesn't seem to be right now. We have emission of radiation whenever we have coherent states. And in a 2D-IR experiment, we're measuring the emission of radiation after the 3rd pulse. So all these coherent states where we're in a superposition, as noted on the Feynman diagrams, they are radiating a field, which is the one that we measure. And in a 2D-IR experiment on the diagonal, all our frequencies will be similar to one another for the measurement. Now, this is a very, very familiar scenario to most people, and this is probably the most common way that 2D-IR measurements have been done in the past. Now, how are we going to do the same thing via 2D-IR-Raman? So look at the same vibrational states, but have a Raman process in there. So what we're going to do is we're going to get rid of the second interaction. We'll keep the first interaction exactly the same as 2D-IR, but the second interaction is going to be twice the frequency. So it's going to excite to this second excited state in 1 step via a transition that in the absence of anharmonicity would be forbidden. And we will also replace the 3rd pulse with our Raman pulse, and then our emission will be in the visible. So if we take this excited state rephasing diagram from 2D-IR, which we're hopefully very familiar with, and we have a Raman transition, which is emitting our 3rd order field, and we've bypassed this population state. So we've taken this pulse away, and we're just going straight to the 2-1 coherence with this second pulse. Then we've got our 2D-IR-Raman method for measuring 3-level anharmonic oscillator. And the emission frequency, I'm going to call omega delta, because we're getting far too many numerals, Arabic numerals kicking around here. And if we look at the emission frequency and we look at when the second interaction frequency is twice the first, that is our diagonal line of this kind of spectrum, the overtone line. And our emission will be shifted downwards in frequency along the axis by the mechanical anharmonicity. And from now on, I'm going to get rid of these numbers because they confuse me. And so by historic convention, I tend to use Greek labeling. So I order the frequencies of the field in order alpha, beta, gamma, delta. So we're going to do that now and use that convention from now on. So omega alpha is the first interaction, which interacts with a 0 to 1 resonance. Beta is interacting with a 0 to 2, and gamma is the Raman pulse, and delta is the emission. And just like in all forms of Raman spectroscopy, where we're measuring a visible frequency, which has some vibrational energy added or subtracted to it, we're going to subtract off the visible frequency so that we just have the vibrational component along our axis of this spectrum. Okay, so that is setting the scene for how we do this. And I should note that this ordering is a rephasing ordering. This is this kind of process that Min Cho was writing about in the paper that I showed you just earlier. And what do I mean by rephasing? Well, that means that this field interaction puts the system into a state that is oscillating in one direction of time, and then this field interaction is putting the system into a state that is oscillating in the net opposite direction. Well, let me show you what that means in a little video. Let's imagine we've got all our molecules sitting here, and let's imagine that they are all oscillating at the same frequency. So right now there's no broadening, they all have the same frequency. And it looks like the video is not starting. Oh, there we go, now it starts. So all the molecules, they're oscillating with dipoles at the same frequency. It looks like something funny is going on with the timing of all this, but let's see them oscillate. Okay, they're all oscillating at the same frequency, and so the average dipole is the sum of all of them, and it carries on oscillating with time as long as these vibrational modes can oscillate for. They'll eventually decay, but now we imagine that all the molecules are oscillating with different frequencies. They go out of phase with one another very quickly, and the net dipole emitted from the sample, the net field, gets less and less with time. So you can see that they're all oscillating away still, but because they're interfering with each other and going out of phase, the field emitted from the sample decays to zero. And what's going to happen in this little simulation is that a field comes in and reverses that oscillation, and you can see that the dipole oscillation of all the molecules averaged together is getting bigger and bigger again until it reaches its peak again, and all the molecules are in phase. This phenomenon for the beginners in this audience is the photon echo, which has been really well known and well studied for many decades. That's my representation of it here. And in IR-Raman spectroscopy, we can measure an echo with the following time ordering for the pulses, because the system can rephase after the alpha pulse, and then the beta pulse can come in and cause the system to, the system will dephase after the alpha pulse, and then the beta pulse will come in and cause it to rephase, and then at some time delay we'll have maximum rephasing and strongest signal, and that time delay is when the alpha gamma is twice the beta gamma delay. Sometimes out in the literature you're using T and tau and things like that. I'm using T alpha gamma for the delay between alpha gamma and beta gamma for this situation, and that is the rephasing delay. We have non-rephasing pathways which we can access if we reverse the ordering of the pulses, and they appear in the 2D-IR-Raman spectrum as such. So actually this diagram here is shifted in the opposite direction in along the axis by the anharmonicity, which is interesting. But we won't look so much at these non-rephasing pulse orderings in this talk. Now for the actual measurements. So for many of the experiments I did, I found it very convenient to look at dried protein films, which I've been doing for a long time under various other circumstances. These films, I adjusted them so that I have a reasonable absorbance in the amide 1 region that corresponds to about 0.3 to 1 micron thickness for the experiments here. And I'm looking at a very classically alpha helical protein and a classically beta sheet protein. And you can see in the infrared absorption spectrum here, the characteristic differences that the beta sheet, the concanavalin A, is redshifted owing to the fact that it develops more states and a wider distribution of them. We're also looking in the amide A region to excite the overtone, but actually we won't be seeing any amide A activity in any of these measurements. They don't show up. So the overtone is buried somewhere underneath these bands, much weaker. The experiment that I did most of this work on was our ytterbium-based lifetime system, which you can read more about in these two papers, and a simple geometry just for focusing all the beams at the sample. We'll make use of the pulse shaper shortly. And it's important to frequency narrow the Raman pulse. And the reason for that is that we can then have frequency resolution in our dispersion axis. So a picosecond echelon narrowed pulse was used there. So here's a plot of the emission signal at 1560 wave numbers, which is nowhere near where amide 1 will emit. So we're measuring a particular frequency in the experiment, and these are the time delays, the alpha gamma time delay and the beta gamma delay. And here is the diagonal line, which would indicate that we had rephasing to an echo. And this is showing us the instrument response because there's no amide 1 emission. But if we move our emission analysis to the amide 1 band, we see a rephasing signal along the diagonal line. And this measurement, so it has many frequency points and many delays, see alpha, beta, and beta gamma. So there's lots of ways of looking at this data set. What I'll do in this slide is I'll take cuts along the rephasing line and plot them as a function of beta gamma. You can see an example here, and then plot those cuts as a function of emission frequency. So this is showing the rephasing, the signal along the rephasing line for bovine serum albumin and concanavalin A. And not surprisingly, they look quite different to one another. But the difference in the concanavalin A signal is not what you expect. It requires a little bit of thought. So we'll come to that in just a moment. But each line here is representing a rephasing signal that is decaying with a certain dephasing rate. And so if we fit along these lines, we can see the dephasing rate across the amide 1 region. And here is the fit error showing that for bovine serum albumin, the dephasing is very well approximated by an exponential across the emission range. You can see for concanavalin A that only in a small region here is the echo rephasing line giving a dephasing rate that is exponential. So the fit error is good around here, but then it becomes atrocious in this region. We'll see why in just a moment. This is quite interesting to me, and I think worthy of a future investigation. Min Cho showed in his paper that if you measure the dephasing rate in this way, using this kind of time scheme and detection, then this dephasing rate is the sum of the 1,0 and the 2,0 dephasing rates. And what Peter's paper told me was that in an exotonically coupled system, these dephasing rates are the same. If you don't have exotonic coupling, then the 2,0 dephasing rate would be larger than the 1,0. So it's interesting to think about what the effect of that would be across this range. So the part of this range that agrees best with Peter Ham and Robin Hochstrasser's measurements of this number for the peptides is here. So at around here, we have a dephasing rate that's in good agreement with 2D-IR measurements, but it's getting less and less as we go across the band. Well, it's known that hydrogen bonding will increase a dephasing rate. That's known from some of Martin Zanni's work. And exotonic coupling as well is going to work in the opposite way. So the stronger exotonic coupling, the lower the dephasing rate, and the stronger the hydrogen bonding, the higher the dephasing rate. So it's interesting to ask, I think, what contributions are happening in these measurements. But I don't have any further answers than that. It's something for future work. If we turn now to why we don't see exponential exponential behavior on the rephasing line here, a good way to start looking at that is to look in a different direction in the echo data. So instead of looking along this rephasing line, we can just look along the beta gamma and alpha gamma time delays. And when you look in that direction, the rephasing echo line is dotted here. That's when we'd expect maximum rephasing. This black line is when we switch over from rephasing to non-rephasing pulse ordering. And we've got them both for BSA and for concanavalin A. And you can see for the BSA that the rephasing peak is following well this time delay. There's rephasing here just a little bit longer, which is interesting. But what I want to focus on here is the concanavalin A, because at early times you can see two peaks at the rephasing line, but there's serious interferences at later delays. And actually, I don't show the data here, but this oscillates in the data as a function of this alpha gamma time. And that's kind of reminiscent of what happens in a pump probe experiment, which is a projection of a 2D-IR experiment. If you have cross peaks overlapping with diagonal signals, then your pump probe experiment gets a little bit complicated. And this experiment is a homodyne detected experiment. So there would be overlapping emission from different processes here and interferences. So ideally a heterodyne detected 2D measurement is needed. Now, is that possible? Something I was thinking about for a few years. We have an experiment that looks like an SFG experiment, but with one extra pulse. In SFG, if we want to do heterodyne detection, a good way is to generate a local oscillator from a reference material, and with the initial excitation beams doing that, propagate everything through to the detector. And this works very well. We do it in our labs. It's a little difficult to make everything really nicely overlapped here and here and here. But I wouldn't be expecting to do it so easily for a 3-beam experiment. And more so, actually, we need to be able to control the alpha gamma delay and the beta gamma delay after we've generated our reference. So I'd have to put wedges in here. And that seemed like a bit of a hassle to me. So I didn't go ahead and do 2D-IR-Raman this way. But there's a nice trick that you can do with a pulse shaper that allows you to do the same thing. And I'd like to show you that now. So we can work in the homodyne geometry still, but what we're going to do is we're going to generate 2 of our alpha pulses. So the first field that interacts with the 0-1, we're going to make a pair of them. Now that looks like Fourier transform 2D-IR, but it's not, because in Fourier transform 2D-IR, this is the first interaction and this is the second interaction. Now in this scheme, these are both first interactions because we're going to generate 2 copies of the signal with these 2 fields. So we're going to generate a very strong field that's comprised of instrument response or non-resonant background. So the pulses will all be overlapped here. And then we're going to generate another field where we are scanning this second pulse anywhere we like. So we can map out the free induction decay of this as a function of time, because we're generating IR-Raman signal from these 2 pulses and this one simultaneously with these pulses. So these 2 signals are going to interfere with each other. And as we scan this delay, that interference will manifest in the signal as an oscillation in the signal, which we'll be able to extract in the usual means that we do for other heterodyne detected experiments. So this would also work for some frequency generation and a number of other nonlinear Raman IR type methods. So it's quite interesting. Here is some protein data. So it's our concanavalin protein film on a little bit of glass. And here's our emission axis. And here's our interpulse timing. And as you can see, we get interferogram as expected. This is a cut along the emission axis. There's the protein signal interfering with the non-resonant background at time 0. And if we do a Fourier transform along our this time axis, then we see this type of 2D spectrum. So this is a 2D spectrum of the amide 1 band, and it's interfering with the non-resonant background. So it sits on top of the non-resonant background, and it's easy just to move the protein droplet out of the way and measure non-resonant background of the glass. And then we divide the glass signal from the protein plus glass signal, and we get a 2D-IR spectrum of our amide 1 band in a heterodyne detected sense. And this pulse ordering, this way of doing it, isolates the rephasing diagram out of the 3 that I showed you that are available. I'll remind you that the frequency axes are analogous to 2D-IR, omega 1 and omega 3. This, strictly speaking, in this spectroscopy would be omega 2. And here's our overtone line, as I mentioned before, and possibly the anharmonic shift here. And interestingly, for the beta sheet spectrum, we have a cross peak. I didn't introduce the diagrams for cross peaks. Here's how it would look using my notation. And the really interesting thing here is that we don't see a cross peak on this side of the spectrum. And I think there's a very good reason why. So if you look at the Raman spectrum of a beta sheet protein and the FTIR spectrum of a beta sheet protein, they're sort of opposite to each other. So in the infrared spectrum of a beta sheet, we have what we call bright states, which are at lower frequency, and dark states, which are at higher frequency. And in Raman spectra that I've seen, this would appear to be the other way around. And with that as the case, we're exciting the strong infrared part of the beta sheet, and then having Raman emission from the strong Raman side of the beta sheet would give us a cross peak here. And if we were to excite the weaker IR part of the spectrum, we would then have to have Raman emission from the weak part of the Raman spectrum. So that shouldn't give us any or as much signal. So that's my interpretation of this spectrum, and it would be really great to see that borne out by some simulation of these signals, which I haven't done yet, but this is the experimentalist interpretation of the data, that it's that the shape of this is due to the Raman strength of beta sheet amide 1 being reversed to FTIR. And this now explains the non-exponential behavior in the photon echo measurement. So we have a cross peak and diagonal peak coming out at the same emission frequency. And so that is interfering with the rephasing process, which is there. And these graphs are the echo plots, but I've turned them around so that they match up with the 2D-IR spectrum. So you can see that along this cross peak part of the spectrum, we have this complexity in the photon echo signal. I alluded earlier that there's a very deep sort of symmetry or connection between this excited state rephasing diagram of 2D-IR and the rephasing diagram of the IR-Raman. And essentially, I'll remind you that we're removing this population step, but the two phases over which the system is coherently oscillating in both diagrams have the same character. And so Fourier transforming along T1 and T3 in 2D-IR gives you this rephasing type spectrum. And the Fourier transform along T1 and T2 that we're essentially doing in this heterodyne detected measurement, again, gives you the same type of rephasing spectrum. So they're really analogous to each other. And you can see that when you look at the much simpler alpha helical amide 1 structure, which is just an inhomogeneously broadened line essentially. And we can see the contours changing in a manner that looks like we're getting a rephasing type line shape here. Taken together, these are the heterodyne measurements that I have, and so alpha helical and beta sheet, and of course lots of work done by other people in 2D-IR, Neil Hunt's group, Andrei Tokmakov's group on secondary structure of proteins, and this is data from Carlos Baez and Andrei Tokmakov. So here's concanavalin A. And this is the comparison in a way of looking at the same system in the two different ways. So this is myoglobin, which is pretty alpha helical, just like BSA. So they ought to be very similar. So we only have one peak in our 2D-IR-Raman. Obviously, you're always going to get two, which interfere with in the 2D-IR spectra. And to see the beta sheet content best in a 2D-IR measurement, cross-polarization, and here we're plotting up to 50% maximum of the signal, and you really see that the 2D-IR spectrum is very different between beta and alpha. So that's definitely the case there too. It's interesting in 2D-IR-Raman that the cross peak is so strong. So those are my comparisons. This is the same hill, but viewed from different sides. And I've mentioned that these are from films and these are from solutions. Can we do all this in solution? The answer is yes. It's a little bit of a convoluted answer. So I mentioned that I did these experiments through scheduled facility time. And actually, I didn't think about doing heterodyne detection first. So my background was in doing spectroscopy the way that John Wright has shown how to do, with these bright picosecond pulses and frequency domain tuning of them. And this makes perfect sense when you're looking at narrow modes, which are weak. So in the group of David Klug, that's how I would do these experiments. So we would have picosecond OPAs and tune the pulses. And we explored lots of weaker, more Raman active bands this way. Towards the end of this adventure, I was finding that there were lots of problems with doing useful measurements in this manner for the things that people in the 2D-IR community are interested in, like dynamics. It became clear to me that it would be nice to get rid of the non-resonant background, which is a real pain, and be able to deal with congested systems or systems where you have fast dephasing. So I started to develop ideas on how to do that. I started learning how other people were doing 2D-IR. There's the pump probe sequence. And I hypothesized, this is about 13 years ago now, this way of doing the IR-Raman, which is to take a frequency narrowed pulse, which we can tune, a broadband pulse, and a frequency narrowed pulse. So essentially this part is what we've already been looking at, and we've had a femsecond pulse here. But my dream back then was to use an echelon shaped pulse, and it would kill all the non-resonant background, and we'd have be able to measure this dispersed on a detector. And that's what I set out to do a couple of years ago. So this is how the experiment works. So we use a pulse shaper to frequency narrow the alpha pulse. And then we have a broadband beta pulse and a narrowband gamma pulse, same as before. And instead of doing a Fourier transform, like in the heterodyne method I just shown you, we scan this. And in the access that I got to the lab over a few years, which was quite tight timing, I took lots of spectra this way because it was easy easy to look at the data. And in this way, I was able to see very early on that solution phase work is possible. So that's a concentrated solution of BSA. I think Carlos's ones that I just showed you were at 20 mg per mil, and we get very good signal to noise. This is from a standard cell D2O. So this, by definition, will work for the photon echo measurements I showed you. And the heterodyne measurements, well, you've got to think about how big that local oscillator is going to be, but that it will work for that too. My problems, which I encountered when I was doing this type of spectroscopy with the frequency narrowed pulse, was that I got very curious behavior as a function of interpulse delay. And I was presenting this data for a couple of years. I think I presented it at CMDS in Korea, and I didn't really understand it. And so it made me smile when I heard Misha Bond last week saying the same thing, because that sort of feeling is one you get quite a lot when you're doing these sorts of methods where you don't really know what you're supposed to be measuring and whether it's right or not. So what I've learned since is that at rephasing times, these line narrowed measurements are well behaved, but at non-rephasing times, when the alpha pulse is longer, you get very weird effects. In this frequency domain mode of measuring, I can reverse the pulse order. I can't do that in the heterodyne yet. You need a pulse shaper on the beta pulse too. But so you can measure the non-rephasing pathways as well, and they're well behaved. For a simple system like BSA, this is okay, but in concatenary A, these oscillations between all these features was very, very confusing. And it took me a very long time to understand what was actually in this spectrum. And it was only really once I did the heterodyne measurement that I could be convinced that that's a cross peak and that's a diagonal signal. So this is a problem doing spectroscopy in homodyne mode in the frequency domain. But I'll just show you one more data set, which is just illustrating the evolution of proteins from alpha helical to beta sheet. And you see, even in the frequency domain mode, as we go higher in beta sheet content, these cross peaks in the non-rephasing and the rephasing are very characteristic. So it's an interesting way of doing spectroscopy through the pulse shaper in the frequency domain. John Wright's point last week, which is a very good one, is about making best use of your pulse energy. So for doing the echoes on the amide 1 band, you're making good use of the pulse energy. The bandwidth is about right for the measurements. But if you're doing if you're doing this line narrowing, you're going to throw away energy that you'd be better off concentrating into that narrow bandwidth. And I've ringed these in red because actually on these protein films, I couldn't take the rep rate higher or these energies higher without burning the films at room temperature. So that's an aspect you've got to be careful of too. But for modes that are much weaker than amide 1, this is probably not the way forward. And as John mentioned 2 weeks ago in his talk, and also we have a fairly narrow tuning range here. So because we have these beautiful laser systems available to book in the CLF, I managed to get time on our TISAF system, which has a picosecond amplifier synchronized to it. So I could have an OPA with picosecond pulses and an OPA with femtosecond pulses. And I wanted to see what that looked like. And it's got a much brighter picosecond pulse. So if you look at the amide 1 spectrum, we're seeing signal sizes that actually saturate our detectors many times over if you do it right. And if we've got a wide spectral range now, and if you zoom in, you can see these weaker sidechain cross peaks. So it's potentially useful for the kind of activities that other people in the field are interested in, like David Klug, for measuring the intensities of these peaks, looking at protein-drug interactions, which is a program of his. And so that's what David and Mike Tarry in the CLF are doing with this technology at the CLF at the moment. So I will wrap up now, and I've shown you actually 4 different ways of measuring 2D-IR-Raman spectra, and we've focused on the amide 1 band because it's got enough interest and enough character to bring out some of the features of these spectroscopies. And I think the work indicates that there's a lot more interesting studies we can make on amide 1 with this method, but actually extend it to other systems as well. One of the exciting things to me is that the picosecond laser systems are not that common in labs across the world. So it makes sense when you've got them and you build a really, really good experiment with high sensitivity. But I know that all the colleagues around the world with 2D-IR experiments, they're using femtosecond amplifiers. And this way of doing 2D-IR-Raman is accessible if you have femtosecond lasers, if you have 2 OPAs and a CCD camera. A pulse shaper is not needed for the echo measurements. It's ideal for the heterodyne measurements. They're just so good to work with, but you could use an interferometer. And obviously making a reverse echelon is best done with a pulse shaper. And there's lots more pulse shapes to experiment with. I didn't mention, this echelon shape, whether it's any good or not, whether it should be Gaussian, etc. So there's lots to explore with this kind of spectroscopy. So we come back to the Y part on the slide, and I hope that the Y part is a little clearer to you now. that we can do 2D-IR-Raman measurements with rephasing and cross peaks in the same way that we do 2D-IR. You know, whereas this is a beautiful smooth mountain, it's a bit on this side. Signal sizes. Yes.
Maybe we should go to questions. I think
times have finished.
In view of time, it would be good to proceed to questions.
Okay, so thanks for your attention. If hopefully you're all still there, we're looking for postdocs to come and join our group at the CLF to do 2D-IR and 2D electronic spectroscopy.
So Chris Cheatham has a question.
Paul, beautiful talk. Good stuff. Yeah, my question is, you know, the one real downside, the kind of trade-off that you're stuck with the approach you've used is that you've got to do this direct overtone excitation. And of course, the cross section for the direct overtone excitation is down several orders of magnitude from the fundamental. It makes me wonder, you know, the equivalent, in some sense, the equivalent approach would be to turn that step into 2 steps, to turn it into a 5th order measurement. Obviously, you're still going to give away some signal relative to just a fundamental transition, but I wonder if you might not win relative to direct overtone excitation. Can you turn it into a 5th order measurement? It seems like you ought to be able to do all of the same things with that 2nd step being a double excitation, basically.
I think that that's a really interesting idea, as you can imagine, it would be quite a fun exercise to write down all the diagrams for that, and maybe with a bit more knowledge from the theory side of what the transition dipole strengths are in all these cases would help to uncover that. So it's an interesting idea, I think. Yeah, and as I was pointing out, as I concluded, that yeah, it's going to be a weaker system, but sometimes we're okay with that for applications in physical chemistry at hundreds of millimolar concentration. There's interesting things you can do.
Beautiful work, thanks.
Thanks a lot, Chris. It's good to see you.
Likewise.
Okay, more questions? Paul, I might have a question, so maybe you can help me with that. So all this rephasing stuff, okay, on their main transition, okay, and then the overtone, they seem to rely on their same, well, correlation function, if you wish. Okay, so because you need to reverse the coherence. When you do it at the same transition, it comes automatically. Okay, here it does not come automatically. Can you comment on that? Would it be some limitation or?
I think it would. I mean, in some cases, the rephasing wouldn't be so complete, right? So if the distribution of frequencies in the 0 to 1 and 0 to 2 for some physical mechanism was less correlated with one another, or then you wouldn't get such good rephasing. I mean, you know, it might be in a system that you've got other experimental approaches to understand. It might be a way of seeing that kind of effect, how the anharmonicity is inhomogeneously broadened.
Exactly, and then the next question, well, because you didn't have any time, but I would like to ask about this Raman microscopy, right? So this is what is maybe one of the most important gains here, right? That you go to the visible, which immediately gives you a pretty nice spatial resolution, which otherwise is quite difficult to obtain with the infrared pulses. Can you comment on that, please?
I think there's an accounts of chemical research by David Klug from some years ago, where he mapped a kidney section using a cross peak of a drug in the kidney section. So it's a nice way of doing it. So it was a long time ago that he showed that you could make images in this way. So My feeling as we went on that, you have Carr's microscopy and Raman microscopy, and it was never clear to me whether, I mean, these signals are weaker and more complex. You want to actually have a killer app for it that you wouldn't want to do with, or couldn't do with Raman or infrared. And I think it's the same for 2D-IR microscopy, that finding interesting problems to solve within the constraints of that method is part of our art, and it excites me when somebody can do that. But your spatial resolution is going to be better with this method, and possibly for things that are cooled so that the damage is minimized. You'll be able to do some very interesting mapping.
Did you look in that regard to what Eric Potma is doing in Irvine?
Not currently. I haven't. I'm aware of his Carr's work for many decades, but yeah, I haven't seen his latest work. This sounds like I should.
Well, maybe if you're looking for good applications, okay, and good system to work on, okay, maybe that would be quite natural contact.
Yes, yeah, that's a good point.
Okay, more questions from the public. I'm looking at their list of people. Don't be shy.
I guess that I'm not really counting as public, but I do have a question. What about using polarization in this type of experiments? Because you could essentially, for the beta sheets, you know that the one transition, the dipole moments of the two transitions are perpendicular to each other, and I would expect that to be preserved when you go to the second excited state, for example.
Yes.
So if you could use some kind of cross polarization, is that possible? And
yes, yeah, I wasn't trying it in any of these sort of proof of concept measurements, but you're exactly right that there'd be this polarization dependence, same as 2D-IR for those two pulses. And if you turn the visible around, you often kill the non-resonant background. Sometimes you kill the signal as well, depending on its origins. But I'd be really happy if someone was to sit down and figure out some of the polarization dependence of this type of signal. Maybe I'd try doing it one day, but that's maybe a couple of months job to do it well, I suppose. But you're exactly right that you have the polarization degrees of freedom here.
Okay, good. No more questions, I understand. Then, okay, thank you, Paul. Then I am stopping the recording.